Now, problem 8 is kind of strange. There's this triangular wedge. It's connected to a handle, okay, right? And you're going to spin it around like this. Now, if you weren't spinning, this surface is practically frictionless. So if I wasn't spinning it, the component of gravity would slide this and accelerate it down the ramp, right? Down that triangular wedge, right? Okay. But because I'm rotating it, right? It's trying to accelerate this way, but I am constantly moving the thing as it's trying to accelerate down. And it ends up, if I do it at just the right speed, it will stay at that same radius out. All right? It'll stay the same radius out from the center. Okay? If I were to whip it too quickly, the wedge would slide out from under and this thing would go flying off the top. I know, it's a weird thing to visualize. Hopefully you can visualize this if you try. So here we go. Child's token is a small wedge, the acute angle theta, sloping side. That's the theta, by the way. That's the acute, that's this angle here, okay? All right, this is meant to be the theta. I had to redo the diagram when I switched over to a Google Doc from Microsoft Word. Okay, anyway, the sloping side of the wedge is frictionless. Mass M remains at a constant height. If it's spun at just the right speed, this height, the wedge is spun by rotating the vertical rod that's firmly attached to the wedge at the bottom end. Show that when the mass sits at a distance L along the ramp here, that the speed for it to stay at that distance L would be the square root of GL sine theta. Okay. So in the solutions, I think I've got an answer document where I worked this out and have it there. I'm just going to work through it real quickly here, so it's on this video, so you don't have to look around different places. And I may go in a slightly different order or something as I'm working through here. That's okay. All right. So let's see. Here is that wedge. Right? Okay. And we're going to be whipping it around here. So this here is like the axis we're whipping it around, yeah? Okay. So here's the thing. If my block is here, right? Where is the center of the circle? Is this the center of the circle here? We are not going like this. We are going like this. The center of the circle is not down here, it's here. Okay? That's the first thing to recognize is the center of the circle is that this is making, the circle the block is spinning around in, is here. So our coordinate axes are going to go this way, this way. Okay? This, right, is the center, the center of the circle is this way, right? This is the positive radial axis, is that way to the left. This is the z-axis, and the tangential is in and out of the page. Okay, that's the way our coordinate axes go for this guy. All right, radial positive is that way. Okay, all right. Let's see. We have that we are this distance L up the ramp. Okay, I know this guy's got a mass M. Am I going to do my force diagram on top of the sketch like this? Whew, that's poor form. That's poor form. I'm going to draw a new sketch. I'm going to do a force diagram, my free body diagram, right? Free from its surroundings. Look, there's that block. Okay. I've got a gravitational force that goes straight down. I've got a normal force that goes up from the surface, perpendicular to the surface of the ramp. And it wants to slide downhill. Will it be a friction force? This is a frictionless surface. So this is it. The only thing touching this, that's it. There's only have two forces. Are they exactly opposite each other? No. This is vertical. This is perpendicular to the ramp. There's a little angle between them. My coordinate axes now, am I going to do along the ramp and perpendicular to the ramp? No, 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 you say. We go along the direction of motion, right, which is into the page. And you say, now we want to go make use of the fact that we know toward the center of the circle, we know that acceleration is the centripetal v squared over r. We want to make use of that fact. So we're going to not do parallel and perpendicular to the ramp. We're going to do along the radius, radial and z and tangential. So what force has to get split into components? Gravitational is going along the z, but the normal force isn't. So the normal force gets split into pieces. Okay, now I'm going to split it up. I'm going to split it up like this. right? Right angle between the components, right? This angle here, the skinny one, is this angle here, the skinny one, the theta that they gave us, okay? All right, this is theta, this is going to be theta, not this. Do you need me to do a little proof that that's theta? You can tell by inspection, skinny and fat angle. You know what I mean? I don't know, is it rude to the angles to call them fat? Probably not. More obtuse and more acute. Anyway, good enough. There we go. So when I split this up, this is going to be n cosine theta. And this part here that's going in the radial direction is going to be n sine theta. Okay? All right, there's my force diagram. Where am I going from here? I'm trying to find what the speed is this thing has to whip around in order to stay steady. You're like, oh, man. Don't know for sure, so we're going to go sigma F equals ma. When in doubt, right? We're looking at, I got forces in two axes here, in the z and in the radial. Let's go ahead and do radial, because when in doubt, we know we're going to do that, analyze that for a circular motion problem. And I'm also going to look at some of the forces in the z is mass times acceleration in the z. When we do the radial, you say radial, it's just that n sine theta. Do I want this to be positive or negative? And you say, well, we know toward the center of the circle has to be positive. That's a positive. My mass, which was given, we were told m, but I notice it's not in the final answer, so I'm going to have to get rid of that m at some point. And I'm just going to substitute in v squared over r, because remember, the speed is what we're trying to find, so I definitely want to substitute that in. All right. So I want to know v. Do I know m? Yes. Do I know r? Well, they didn't tell me r exactly. They told me L, but I can figure it out from that. Do I know theta? Yes, they told me theta. Do I know n? No. So you're like, son of a gun. I'm trying to solve for v, but I've got two variables here I got to get rid of, right? I got to get rid of r and I got to get rid of n. M, n. And if I cheat and look at my answer here that I'm trying to get to, right? I don't know if r or n in them. I got to get rid of those, okay? Oh, look, there's a sine theta, sine theta. That's a good sign. It's a good sign. All right, never mind. Anyway, looking at this, I got to get rid of n, and I got to get rid of r. Okay, which one do you want to do first? Me too. So r, can I find the radius? Now that's the distance along this axis from the axis of rotation here, right? That we're whipping around. It's from the center of the circle here, this length. Now look, do you see this? Look at this. This, I shouldn't draw there. It'll be the same thing as this, right? This is r. And this is L, and this is theta. You're like, oh wait, look, this is a right triangle. R is this horizontal bit, and L is the hypotenuse. So you're like, oh, and this, look, this is the side that's adjacent and hypotenuse. Oh my gosh. You're going to say, look, I can see just from the sketch, right, looking at lengths and stuff, that cosine theta is going to be adjacent over hypotenuse. That's going to be R over L. Therefore, R is L cosine theta. And now I can get rid of that r by substituting in L cosine theta. And so you say, okay, I'm going to come back to that. So am I allowed to have L in my answer? Yes, I am. Am I allowed to have cosine theta in my answer? I'm allowed to have theta. I don't know how I feel about cosine theta, but we'll see. Okay, now we got to get rid of n. Where else am I going to get the normal force? You say, well, that's going to come in here too, right? When I look at the z-axis, I'm going to have an n cosine theta. Ooh, maybe something magical will happen there. You say, so let's look at the z-axis. I'm going to have up minus down because I'm calling up positive. So this will be n cosine theta minus mg equals, now what's the acceleration up and down? This is not changing its height on that ramp, right? As it goes around and around and around, it's not going up and down at all. That vertical, that acceleration in the z had better be 0. And so there we go. So I can see that n is mg over cosine theta. And I can substitute this where it says n. So doing that substitution, I will have mg over cosine theta times sine theta equals m v squared. And where it says r, I'm substituting in this L cosine theta. Mathematically, we say, hey, look, there's an m there and there's an m there. There's a cosine theta there. There's a cosine theta there. Bam, bam. I'm trying to solve for that speed. I'm just going to move the L over there and take a square root. GL sine theta square root is V. Ta-da! That is what we were supposed to show, that the square root of GL sine theta is that speed where the block stays still. Ta-da! All right, I enjoyed myself. All right, hey, that's that problem.